Hi everyone, today we're going to analyze a problem related to a reversible turbine. So let's get started. Same thing as before, I'm going to start highlighting information while I'm reading. Okay, so error at 400 kilopascal, 970K enters a reversible turbine operating at a steady state, and exits at 100 kilopascal. And 670K. Heat loss from the turbine has an average outer surface temperature of 315K at the rate of 30 kilojoule per kilogram of air flowing. Kinetic and potential energy effects are negligible. For ideal gas, the CP equals to 1.1 kilojoule per kilogram K. Determine the following. So this video we're just going to answer the first question, the rate of work developed per kilogram of air flowing in kilojoule per kg. Okay, so first we're going to list our assumptions, of course. So from all these highlighted phrases, we can assume that first it's a steady flow. Also, it is a reversible process because a reversible turbine, so it's reversible. Also, the kinetic energy and the change of potential energy, they're all zeros. And also, of course, it's ideal gas. Also, CP is constant. Okay, so now we have all these assumptions. Cool. So if we want to answer the first question, the rate of work developed, so this sounds very complicated, but essentially, here we have this little hint here. It's essentially just we need to solve for W dot out over M dot. Okay. And sorry, my handwriting is not very good because this pen that I'm using is not very comfortable. I apologize for that, but I'm going to try my best. So, whenever we're dealing with steady flow devices, we're going to list our steady flow energy equation. So, I usually like to list the entire equation, even though sometimes it's very long, but I think it will help you eventually. So I'm just going to write it out. So m dot delta H plus P plus K is equal to Q dot minus W dot. Okay, so our goal is just to change this equation into a form that is W dot out over M dot. And that's actually not that hard. So first, let's cancel out, or let's just eliminate those terms that are not very useful. So P, K, zeros, cool, like this. So now we're left with just M dot delta H is equal to Q dot minus W dot. And if we move this W dot over and divide all these terms by M dot, it's going to be like W dot over M dot is equal to Q dot minus which term? Minus delta H. Okay. And if you notice, actually, I forgot to divide M dot on this term. Okay. So Q dot M dot is given, which is right here. This is 30 kilojoule per kilogram. However, we don't know this delta H. We don't know this directly, but we can calculate for that. So let's just put here. So W dot over M dot is equal to, pay extra attention on this M dot over Q dot over M dot form. So it is a heat loss if you read this carefully, this is heat loss from the turbine. So this term is actually going to be negative. So we're going to just put a note here. This term is going to be negative. Okay, so now we can write out our equation again. So it's Q dot over M dot and minus delta H can be rewritten as Cp delta T, so T2 minus T1. And in this case, our T2 is, so T2 is here, and our T1 is this 970K. Okay, so now we have everything. We just need to plug and chug. So, like we said before, this term is negative, so we're going to put negative 30 in here, minus 1.1 times 670 minus 970. And this will give us 300 kilojoule per kg. And this is for part A.